Hi, everyone. Okay, so hi. My name is Pedro. I'm a PhD student in Aalborg University in Denmark, enrolled also in Robert Bosch Corporate Research in Germany. My supervisors are Nikolai and Peter Popovic and Beatrice Sohe. Yes, you all know them. So my presentation today goes a bit in the direction of the very nice presentation of Marius, right? We had from Eurocon some days ago, this sense of goal-oriented communication. So I really hope I can build a presentation, complementary presentation top of that, showing some applications on that regard. Well, don't need too much introduction about that. We all know about Industry 4.0. We have this concept of wireless message digital services. And one application that we search in this context is to offload some control functionalities to the edge. So basically, I have some control applications, drones, AGVs, and so on, and I want to control them in the edge because there is some advantages financially, also in terms of performance, and of optimization, and so on. And this is today not possible. Let's put it like this, not with the technology currently have. So that's why we do research. Well, there is actually a very interesting application, Bosch. More specifically, you have this automated valet parking. You basically leave your Mercedes there, and it autonomously park your car using fully controlled by the wireless network, send command and so on. Very interesting. There is in Stuttgart in Mercedes Museum. So, but what's all that about? So we have a traditional control problem, actuator, plant, and sensor, and a controller. And basically, there is a wireless in the middle. And that's when everything changes. Because then we start to have some state estimation from the sensor. We start to have some delayed control input. And of course, it affects the stability of the plant. And of course, on top of that, we must also control how much resources we use. So every problem like this is basically a research area that people spend the whole career studying control theory, network theory, and so on. And one thing I realized specifically in this area is that these two domains are very separate. The control theory and the communication theory, they do their own optimization. So basically from the control perspective, they see the network as a kind of fixed behavior, random behavior, and they optimize the controller. And for the communication, we see this as a requirement, as a table. So yeah, and everyone does its own solutions. And what I tried during my PhD is to kind of unify them a little bit. And this work in summary is basically two works, one in a conference and other in a letter that recently published. So I'd like to just give a quick introduction about age of information, but there's not really need to. It's just the current time minus the time in which the process was generated, because we already know, so you can skip for time purposes. And the importance of that is that AOI has a kind of intrinsic limitation. I can only measure by one link. And if I want to optimize something, I must separately optimize either the downlink or the uplink. And if I combine both, it kind of needs a perfect feedback in both directions. So in control loops like this, I mean, I can either optimize AOI here or here. So, but this whole process is a kind of loop. Everything depends on each other. So the behavior of this guy kind of impacts the behavior here and vice versa. So for this reason, we propose along the PhD a new metric that we call age of loop. So basically in this case, it's very simple. Also the idea, my sensor process start to generate something, right? Sensor value, position or something. It goes through the whole communication process, queuing and so on. It arrives to the controller. It can take some time for the controller to provide some control action. And then this information is passed back to the actuator. And here I measure the AOI. My time is reduced. So basically during this whole process until my information is received back. So I ask for help. And when I receive this help, I kind of diminish the time specifically. And it looks like that using this, it's a bit more useful for this kind of application. Yes?
What happened to that case? Why did you drop it?
So it drops by the time in which this process was generated. So let's say I generated it here, and the time is going on. And then when I receive, so ask for help, the times goes up. And when I receive help back to the controller, I diminish by the time in which the process was generated. It's like AOI, but the whole loop instead.
Still, I don't get why you would draw P3.
Where, more specifically?
P3, right?
Okay, it's because we can basically calculate in two directions. We can use from this perspective, to this plot, and this other perspective, which is like this plot. So basically, I send a control command, and I wait for the feedback of the sensor. So then I start to count here. So I start like say in T1 heads, and then when I receive it, so the time keeps counting. And when I receive the command back, I diminish by the time in which it was generated. So at this point, I diminish by this time.
You must be wrong, right? Because you have an arrow starting from P3 that's, you know, if you look at the drawing on the left-hand side, you see P3.
Yeah, here or here?
Top,
Top,
you have
okay.
an arrow that goes down to the controller, and then you can see that.
But maybe the controller is responsible. One or another. Usually the controller receives the command that is issued. So the example is issued with the P3, but it's not.
Yeah.
Actually, you have P3 prime going back to the actuator later on.
So
I can't read the figure on the left, right? Because you have this arrow starting from P3 and going to the controller. Then you have another arrow starting from P4 and going to the controller. And then apply is P3 prime.
So the question is, or maybe you're just the number in the numbers above and below, and you don't have to correspond to each other. Typically. You're just doing the sequence. And then whenever you do something, you set you create the sequence number. It's the P3 prime doesn't have to do anything with P3 over there.
so look in this perspective.
Yeah.
I received something, right? Let's say P2 prime that we talked about.
Yeah.
Let's say here.
P3 prime.
So here I received something here, okay?
Yeah.
So in this time, P2 prime, I diminish by the time in which the process was generated, which was P2, right here.
Yes.
That's it. Follow this logic.
So what the thing is that P3 prime
Huh?
doesn't necessarily have to be anything to reach the P3 in terms of numbering the comments.
No. Okay, you got the point. So, yeah. Let's talk about an application of this. I can actually, I'm just explaining a little bit what is the actuator plant and the sensor. It's actually a traditional control problem. We have this quart pole that we use a lot in reinforcement learning. Here, the system dynamics. So basically, you need to apply a force to the car to keep the system in equilibrium. It's a good example. We use the benchmark for some control applications because it kind of requires fast control cycles. So I need to send it the information, uplink, downlink quite fast to control everything. So I'm controlling this wirelessly. That's the point. In my controller, there is a sequence of steps that I need to define. First, we have the state space, which is the position and the velocity, and the position of the car and the angle. I linearize the plant to make to obtain the system, the following system dynamics, and the optimal control is a kind of linear function. And then I define a control cost, which is the linear quadratic regulator case. It's traditional in control theory. And then I solve this using the algebraic Hikachi equation. And then I obtain the optimal controller. That is basically control theory, what we do in normal circumstances. And for the wireless communication part, it's basically an inspiration from the Alvaro from Nokia. He had proposed some reinforcement learning challenges some time ago. And I basically use the same model. So let's say we have some age of loop for the plant, certain CQI, a certain buffer of data to transmit. And my node B has a certain maximum amount of bandwidth. So I need to decide how much bandwidth I shall allocate. And depending on the CQI, I can directly verify the 3GPP table and check how many bits I can transmit. And then I reduce from the buffer. And after everything is received, the information is received. Backwards, the controller, you send back the command to the plant. And this is basically a gamma distribution. And I'm going to explain why, because this is something interesting that we observed along the work. So in this kind of application, the uplink in general requires much more, say, heavy data load. Because I'm sending here LiDAR information, video camera, and so on and so forth. The controller, on the other hand, is like a direction. Left, left, go right, up, down, stop. Always like this. So it really looks like an ICMP packet. And what we have observed, actually, on some real measurements inside some Bosch factories, is that this behavior, okay, tends to really concentrate around an average. So the whole loop takes like 20 milliseconds. But if a long tail, that we don't actually know how to explain why. So what we have done in turn was to use, let's say, probability density function approximation using the residual sum of squares as a KPI to kind of obtain the best distribution to model this behavior. And interestingly, the gamma distribution was the optimal one, which goes in the direction of other works that explore LTE and Wi-Fi that also obtain a gamma distribution. It's the same for 5G, non-standalone. Or actually standalone.
Why didn't you use a mixture of distribution?
Yeah, because I mean, I didn't think it was quite simple. There is some squares are already enough to model quite precisely. So I think it could be an overkill. I mean, but I may be wrong.
So this is the distribution of the uplink, or it's the uplink.
Yeah, downlink.
Downlink.
Yeah.
And
So-
is it a shared channel or is it dedicated channel?
Dedicated channel. It's 5G standalone,
There is no interference.
not theoretically. So and that's a good point, because you are sending small amount of packets, you expect to be always precise,
Yeah.
but that's not the case in real scenario.
Yeah.
And the question is, should we model this? Should we include this behavior in kind of solution?
Okay. Because they use gamma for some other stuff, but not.
So what we want at the end, let's put like this in these terms, is that I want a function that, given my state of the age of the loop, I want to have a kind of expected control performance. So this is the first time I'm talking about a network KPI becoming a control KPI. So I have this loop age, and based on that, I want to have an expectation of my control performance. So when I mean control performance, I mean the LKR cost function, which is a controller cost function they use in control theory. Let's say this is possible. I'm not sure yet if it's possible, but maybe it is. Okay, if you have a look, this is basically the definition of a value function, right? I want a kind of certain state, and based on that state, I want to obtain an expected cost function. This is basically the expected reward that we have in reinforcement learning. And we can actually evaluate this analytically, which can be a bit harder because this relation of AOL, which is first defined, and the LKR is not yet studied so much, but we can actually obtain it by empirical evaluation. So you can test your environment multiple times, obtain some data samples, and by temporal difference learning, you can approximate this value function. And after doing this, a kind of interesting result appears. This is the cart-pole environment as a function of the age of loop. And here this expected LKR performance. So of course, if you are in 0 AOL, your system is perfect. Your cost function is amazing. It's perfectly aligned and so on. As we increase the AOL, the performance starts degrading. Makes sense, but not so much. So because of the controller, the system has a kind of robustness against this latency. Two things I can conclude. I don't need 1 millisecond latency requirement from 3GPP. I can wait a little bit, 10, 20. The system still works. It works, of course, less performance, but works. But after it gets to 40 milliseconds, things, it loses stability. So I'm within the stability region up to 40 milliseconds. Afterwards, my system breaks.
This is a great problem.
Yeah, and here actually a question like, if you are the network engineer, I'm the control engineer, and I give this plot to you. I mean, what you can do in turn, like to optimize the network. So I can, for example, always create regions of criticalness, and my network can interpret these regions and take decisions. Based on that. Yeah.
No, but it's not it's you didn't expect it, so there can be cases where you have less than 40 and you lose stability.
It depends on the application. So
But the results are expected, so it doesn't mean that it's never maybe the age of totally or pending, never lose stability. You can have one that open. But there was
Some kind of method.
when it's not
yes, so just to complement, 3GPP actually provided something in that direction. It's called survival time. Survival time. So in the standards, we can basically define the survival time of your application, and it basically says that, okay, you can send with some delay, but not more than that. And it's basically what learning the survival time here.
And the problem then is that they don't use this probabilistic method.
Mhm.
Real probability. So, and they are, I mean, well, really, I guess they don't really have a use case.
How did you get this? I mean, have you simulated different age of loops?
Yep.
And but do you assume that the different delays are independent of one another, taken from the distribution, the gamma distribution before? Or have you taken some real trace of delays from?
So in the simulation, you can kind of force the delay to be always, I can kind of force to be the age to be always around this point. And then based on that, I can evaluate the value on that.
Yeah, but you assume that the delays of the different communications are finally.
Yeah.
Independent and identical distributed. Have you verified this assumption when you plotted the empirical PDI of the delay, right? And you observe that it's communicated, that's fine. But maybe, you know, let's say, let's call it anomalous delays, the longest one, are not independent. Where you might observe, you know, very short delays for a number of communities, and then maybe the state of the system changes, and you have a series of long delays. In that case, the stability of the system is more critical, right?
You're gonna get there. So we're gonna get there. So yes, given this age of this state of AOL, I can have this value function of this age and have an expected control performance. So let's use this to optimize network resources. So the idea first is pretty simple. I have this wireless control system environment, which is the Cartco example that we showed. And I need to find a bandwidth allocation policy among a certain of options, which is the action space, like this. And my reward would be like, okay, the control cost, LKR, plus a penalization for the amount of bandwidth. Because there's just one user, then makes sense that, okay, try to minimize the control cost using the minimum amount of bandwidth. That's the whole point.
Sorry. Sorry.
Yeah.
But the point very interesting. So the penalty term there is the sum of BI over BN.
Yeah, so it's because like this.
You know, you want to use the minimum value.
Yeah. The minimum bandwidth, but weighting the control cost as well.
Yeah.
Okay. So what BI, sorry? Again?
Yeah, is the so I have different set of bandwidths. 100 kilohertz, 200, 300, and I must decide for one. And every time it uses one of them, there is a penalization by the its next. So 0.1, 0.2, 0.3. So I'm basically summing up the bandwidth usage in conjunction with the control cost.
Right, and the sum there for I, what is I?
It's the option that you can use among any different. I belongs to N.
The question is, you have a sum there.
Yeah.
I go from 1 to 1.
20.
It's like,
That is a constant, right? And if I go from one to it, and it's not just.
It varies on the policy. So the policy we decide for I, and every time it's not.
So you have a, okay.
Okay.
You use, probability of choosing the I.
Yeah, exactly.
It's 5 here. So it's the number of times you select the I over the four possibilities that are available. And Bn is the maximum value that you can have.
Yeah, exactly.
So basically, if you put something, like I go from one to something, and that something will get
Yeah, probably.
for the soup, right? Probability of choosing the I.
Yeah, so we solved one of the problems I named DP, we solved using temporal difference learning, key learning, for example. And yeah, so we focus on this problem, a benefit allocation policy, but I guess this could be extended to kind of packet length or antenna configuration. So just to provide some previews about before the results, we compare this approach, we fix the requirements, which is basically what we have in industry, transmit anything with 1 millisecond delay requirement of 5 milliseconds, 3GP defined. And multiple channel qualities, and also random sensor samplings, because my sensor of the plant can also changes among different applications. And we have obtained the following results. So basically, this reinforcement learning scheme, I could say the most amount of bandwidth compared to fixed bandwidth requirement. So like this, if I always transmit within the requirement of 1 millisecond, I'm going to spend a lot of bandwidth, or 5, even less, and 10, and the reinforcement learning scheme, I could achieve the smallest one. And here comes the more interesting part. The control cost of the reinforcement learning scheme is a bit higher. And the question is why? So I saved more bandwidth at the cost of having a higher control cost. And if you look at the plot of before, around -8, my average LKR cost, it's basically this point. So my algorithm, the algorithm, it basically learns and exploits this behavior in order to save bandwidth. So I'm exchanging here bandwidth for control. That's all. I mean, this is interesting.
Doesn't depend on the way you weight the different parts in the.
Depends.
Little word.
Depends. So what does it mean? I'm waiting this region, but I could force to be here. So I could push the criticalness of the.
and the bottom instead of the sensor sampling, we have random sensor sampling.
Yeah.
To be varied by different values to be.
I put like 1 millisecond, 5, 10. Yeah, so this is one of the first works. We have also extended this to a multiple user scenario. We have published some other works on that.
No question. So what happens like, let's say you force by using my Q1 shaping, you force your page of loop to be like around 10 seconds. It's like the LKR cost of the RL scheme around the same, but it's like better in that case.
No, it's what's going to happen. The LKR is going to diminish, but the bandwidth usage is going to increase. So we expect to see the opposite behavior. Maybe it's going to increase a little bit, and this is going to.
Okay.
And that's the point, because depending on the application that you want, maybe you don't care too much about this LKR. Maybe I mean, you are satisfied that your robot is here. Depending on the, and maybe not, maybe the application is critical, we want to be here. The reinforcement learning scheme can kind of. So yeah, so just as a continuation of this work, this is another work that we submitted to a IEEE wireless communication letter that we explore now the same concept, but from AGV, which is more realistic for a factory. There is many AGVs in Bosch. So basically, the application is very simple. We have a vehicle that must do a kind of path, bring on object to another place. So there is the metric that we are interested in, the track error. I don't want my AGV to go out on the track. So I always have a reference track that my AGV control. And if my AGV is too far away, that's bad because it can collide with someone. So I'm controlling this AGV from the edge. There is a wired network in the middle, which is a problem. The states of my system are the positions of the AGV, the angle in which he is, and the velocity. Here's the system dynamics. I basically linearize and apply the Taylor approximation to have the system dynamics every time step. And then I use optimal LKL controller as before. So I'm interested in taking the difference of the position, this one. I have the X error, and I have the LKR cost, and I solve the algebraic Riccati equation to obtain the optimal control, which is the acceleration and the angle delta. This delta here will impact delta. So I move the AGV, and the acceleration impact the velocity. So the idea is very simple, like the same of before. I have the whole process again, the random delay here, but now a fixed one and a gamma distribution. But we have a different thing, the data rate policy. We provided a more realistic channel model to this application, which is basically the first order Markov process. It is very good to model correlated channel. So my channel can be in good or bad state. So my transmission is successful. It impacts my next transmission. So I have a correlation between these transmissions, model the Markov that we talked before. And this has interesting probabilities between each state. I'm going to use them after to my solution. And here there is a very interesting trade-off that is studied in channel coding. Basically, I can transmit, let's say, like it's put like this. I have a certain amount of bytes to transmit. If I select a high rate, the transmission time will be very low. I mean, I transmission my information faster, but at higher risk of packet failure. On the other hand, I can wait a little bit more. I can increase the packet length, or I can decrease the rate. The transmission rate in this time will be higher. I wait a little bit more to transmit, but the packet error probability is smaller. So there's a trade-off. No more. And the point is, what is the best trade-off to this application, this AGV, considering that we are interested in the track error? So the point is, I must select an optimal data rate for this problem. Well, okay, this is a kind of lemma that we defined along the paper. Basically, using the stochastic approach, you can model the system dynamics as a function of AOL. And since the solution of the control optimization is unique, the track error is asymptotically non-negative with relation to the AOL. I better check the paper to verify the proof, but the main impact of this is that what I'm stating is like this. If my path is very stable, it's rectilinear, I need less resources. However, if my path is starting to make a curve and it's very complicated, I need more resources. That's what we can analytically verify. And what I find interesting on that is that for the first time, I'm taking, let's say, I'm considering network resources, not targeting some network API, age or KOS or something. I'm checking the necessity of network resources based on the trajectory of the AGV. So this application of network aiming the control, at least the first steps of that. So the problem is, once again, quite simply formulated. The AGV environment, I have a track error. I observe my AOL and my channel correlation state that we discussed. Based on that, I select my data rate for a certain amount of bits. I have my optimal control, a random delay, and then the whole process continues. Since I know the dynamics of the statistics of the everything, basically we analytically derive the AGV track error as a function of AOL. Then we formulate the problem as a semi-Markov decision process, and we solve using value iteration. We don't need reinforcement learning here. Here's the policy that we obtained. I particularly think this is an interesting result because it compares how my decision, how much rate I select based on the two states I have, the age of loop and the channel being good or bad state. So if my channel is in the bad state, so my channel, I have high probability of error. if the age is small, my agent doesn't really care about missing, say, information. So basically, I can risk if I'm increasing this region. However, as my age increases, the error rate starts to decrease as well. Which basically it says, okay, if my age is getting higher, I better risk less and transmit with less probability of packet failure. However, if the chain is in a good state, it's just risk and just transmit the way they want.
This is both, I mean, for your channel, good state about state, you, I mean, this result, you can allow some error, even low errors for high errors, it's not to be like perfect.
Yeah.
You know, for one, so that works also for.
Yes, exactly what I said. So it's like I can miss, but I don't care if I miss. What I care is that my track error is always within some boundaries.
But it depends on the actual value of that error, right?
Yeah. Value of what?
And I was.
Okay. Okay. So this is the obtained policy. Okay. So, okay, if I try to transmit very high data rate, the probability of error is higher. So I'm risky. If my channel is in a bad state, like if my age of loop is small, the track error is also controlled theoretically, and I can risk to have a high data rate, transmit very fast, high probability of packet error. However, as my age of loop increases, it basically means that my track error very probably is going to increase as well. So I can't risk. I need to transmit safely. So it reduces the data rate to diminish the probability of packet error. If it's a good state, not unless the age of is high. Yeah.
Why when the age of loop is around 105 seconds, the strategy with the bad channel is more aggressive than the strategy with the good channel?
Yeah, that's a good point. That's just, I mean, how the policy was obtained. And then it goes a bit in the direction of Mateus. They think to interpret what the agent is doing, why it's doing, interpretable AI.
Different realization.
Yeah, of course. Actually, this is the optimal solution. It's valid iteration. This is the optimal policy. It's not realization here. I saw analytically.
Okay.
So to compare this policy, we have a baseline. This is actually a work in actually the same letter that they only use AOI instead of AOL. And yeah, we compare the track error of its solution, more specifically the highest percentile, because I don't care if the error is within some boundaries. I just want that GV doesn't go at peaks of track error. So I check the highest percentiles and compare with fixed data rate policy. So I just have a fixed data rate all the time, or I use a kind of AOI only solution, which is this other paper. Actually, the guy talked to me by mail. Yes, here the performance. I don't like this plot here in presentation, but I'll try to explain. Okay, we have some different sets, fixed data rates with gamma and fixed delay, the proposed solution, and the baseline, and the ideal communication. And here's the 99th percentile of the track error. If the communication is ideal, perfect. So no delay, no packet error. My track error is almost minimal. There is only a small amount because of the controller itself. If I have a fixed delay requirement, the performance of the proposed solution baseline are more or less the same because the AOI and AOL are more or less the same. So there's no much difference, just a small amount in this case. And here comes the best part, because when I have a gamma delay in the downlink, then the performance is like really changed. And comparing the all proposed solution and the baseline, that's when I have the most gain. And the fixed delay requirement for the fixed approach that have fixed data rates, how much you can obtain. If I have this data rate, this performance, this data rate, this performance, and so on and so forth. We can have an example of the trade-off that we talked about of latency and reliability. If I try to transmit very slow, it's bad because the transmission duration is very high, so tracking error increases. If I try to transmit very fast, have high packet error, so it doesn't work. And I have an optimal fixed policy somehow. Transmit at the time the same. And here's more or less the gain of our solution compared to the baseline one. So the highest the percentile, the highest the gain that we have, which shows that we gain what we need is the highest percentile of the track error. Yes, that's it. I was on time. Yes.
The problem where these papers by the people whom that have this valuable information for you to talk about.
Yeah, I've seen that.
Over there, the method basically seems to function linear. There is no linear.
Yeah, also in KTH, they have some work on that.
I mean, they collaborate.
Yeah, okay. And I actually tried to do some reinforcement learning on that perspective, and the result was very similar to KTH. They kind of keep trading off controlling communication like zigzag. It's like the optimal policy always go toward this way.
But what I'm trying to say over there, basically, because the function is equal, basically linear. I mean, then minimize DOI is more or less the same thing as minimizing DOI. It's different.
They think you are.
For you connect, you need USB-C. The cable, I need one thing.
Hi everyone, I'm Parham and I'm from Aalto University. My thesis is about channel chart-based beam management, and I'm going to give a summary of my PhD thesis here. I think it's not. It seems that it doesn't work. So today I will give an introduction to beam management problem in 5G new radio, and then I will talk briefly about channel charting, which is the building block of my PhD thesis, and then I will talk about different scenarios and numerical results that we get from them. So first of all, in 5G network, millimeter wave communication is a key enabler for higher data rates, but it's susceptible to frequent blockage and high shadow fading. But thanks to the short wavelengths, we can implement large array antennas there, and we can benefit from narrow beams with high beamforming gain. But it in turn introduced some new challenges, especially in beam management, where we define beam management as identifying and maintaining the best beam pair between the transmitter and receiver. So 3GPP standard for beam management has introduced beam sweeping or exhaustive search for finding the best beam pairs, but it has a high overload and impose lots of control signaling to the system. So motivated by recent advancement in machine learning, where it showed lots of gains in optimization of wireless communication, we were motivated to examine the idea if we can have a data-driven beam management. Also for beam management, by using machine learning, some new works has used site information in the radio network access, such as location information or other sensors like LiDAR or radar. But here we just want to focus on only information in the radio access network so that we don't impose other site information to our communication. So as we may know, beam sweeping, for the beam sweeping, we have a 3-stage process. So in the first two, we first find the best beam for the base station. And then after finding the best beam for the base station, UE finds the best beam for each of the base station beams and then reports the best base station beam back to the base station. But it's imposed, as I said, a significant signaling overhead, and especially during beam tracking, where we have different refreshing criteria for doing the beam sweeping, we may face some problems because in the beam tracking, first, after doing the first beam sweeping, then we will have for each time slot one base station for base beam, and then the UE finds its best beam conditioned on the base beam that it gets from base station. And in the next time slots, when the base station receives the pilot signal from UE, when it wants to estimate the channel and find the best base station beam, it is conditioned still on the previous time slot beam. So as I said, especially when we have multiple antennas at the UE, then because at the UE we assume that we will have an autonomous beam forming, meaning that at each time step, the UE only reports the best base station beam and not its beam. So the base station might lose the track of the best beam, and it may transmit toward the wrong direction. So especially our objective here is to just find the best beam for base station only by doing the measurements at the base station. And to do so, we resort to data-driven methods so that we can learn the environment and find these best beam pairs. So as I said, we use something called channel charting. Channel charting is actually a mapping from CSI to so-called channel chart, in which nearby data points on channel chart indicates nearness in physical location. In other words, somehow channel chart encodes relative locations of UE into a chart. So as an example of channel chart, here we have the UEs with their physical location and annotated with one beam SNR. And then on the right-hand side, we have the channel charts that we get for this environment. And as we can see, the neighborhood information is well preserved. So we can use this channel chart in cognitive tasks that does not need exact location information. So like handover or beam management, we just need to know the areas where we have the dominant beams.
Sorry, just to understand, because this is a key point, I think, of your presentation, right? So I want to understand it clearly.
So the graph on the left-hand side is basically the received power in different positions from a certain page, right?
Yes.
While on the right-hand side, what do you do?
This is the channel chart that we construct from the received uplink signals. And then we just annotate them again with the SNR at that beam.
With the SNR?
With SNR of the beam, we annotate the
Okay.
other picture, the other figure. So
Oh, right. I think the problem is that I cannot read what you have written on the x-axis and y-axis on the right-hand side chart.
this is only the x-axis on the physical location. This is x and y. It's a straight segment. But this channel chart, it has, again, 2 dimensions. So let me just explain what is channel chart. For making a channel chart, we receive the uplink signals. Then we we make the covariance matrix for each UE. And then this would be our feature. Then we use the dimensional reduction techniques to make these channel charts. So the conventional way is that first we have the feature, and then we compute the pairwise dissimilarity between different features, which is covariance matrices. And then after having the pairwise dissimilarity between all the UEs, we use a manifold learning technique, or maybe very simple dimensionality reduction like PCA. Then it will give us a chart, which we call the channel chart. So as said, for channel chart, we can use either linear dimensionality reduction or linear ones. But when we use the nonlinear dimensional reductions, we can preserve the local neighborhood information well better. So for example, in here, this channel chart is obtained from a TSNE dimensional reduction. So how we want to use this channel chart for mobility management in 5G networks? First of all, in 5G networks, we have both inter-beam and intra-beam handovers, meaning that we have beam level mobility and cell level mobility. So as an example, for example, if you want to have the beam mobility, the beam level mobility, we want to do an SNR prediction based on the channel charts. So we first, in the offline phase during the training, we construct channel chart for each beam based on the received signals, and then annotate each of these channel chart locations with SNR of all other beams. So now we have a data set of channel charts and all SNRs. We only need to train a model. Given the channel chart location, it estimates the SNR at other beams. Then during an online phase, when a new UE comes to the environment, first based on the covariance matrix, after the initial establishment, connection establishment, we can estimate the channel covariance, and then based on the different channel charts that we have, we locate this one on the channel chart, and then by using our SNR predictor, we can predict the SNR of that user at other beams, and then accordingly we can decide whether we need a handover or a beam change or not. To be more precise, on the online phase, we have the CSI, and we have different methods to do the channel chart or just process this CSI. First of all, if we use, for example, a PCA, we could directly find the channel chart location. But if we are using nonlinear dimensionality reduction, we face a problem. It's the out of sample extension problem. And if we want to have the out of sample extension for nonlinear DR, we have to compute the dissimilarity between the new user to all other existing users. So, and it will be a heavy computation. So we devised an adaptive sampling set reduction, and so that we, by using less dissimilarity, by using less dissimilarity calculation with other users in the training phase, we can reduce the computation complexity. And then once we have the channel chart, we can use different SNR regression, such as from K nearest neighbors or GPR or neural network to find the SNR. So as I was saying, the out of sample extension, for this we assume that when we get the channel chart, when we get the channel covariance matrix, in order instead rather just somehow comparing this covariance matrix to all the existing users in the environment, we do a telescopic method, so that in each stage we only calculated the similarity of the new user to a set of users which are most close to this one. So we can somehow a bit reduce the computation complexity of this out of sample extension. So far, we were using this channel chart based SNR prediction for standalone system. We can extend this to non-standalone systems. The only difference is that here we have only 1 sub-gigahertz base station, so we can construct the channel chart for this sub-6 base station and then annotate it with beam index from millimeter wave system, and then we can do the same beam prediction based on the channel chart that we get from the sub-6 gigahertz base station. And also in another part of the board, we can use this channel chart based SNR prediction and use it for the beam tracking problem. So we follow the same procedure as in beam tracking, meaning that first we have a beam sweeping, and then in the next time steps, we will have, when we want to estimate the channel at the base station, instead of when we want to, after estimating the channel covariance matrix, we can just use this channel covariance matrix to map the UE on the channel chart, and then based on the trained channel chart, we can find the SNR of that user at other beams or other base stations. So here we can somehow fix the problem when we had a misalignment between the base station with the new base station beam. And that's it. And as for the numerical results, the simulation setting that we use Quadriga simulator to generate CSI, and we follow the non-line of sub scenario that was 38.901, and we put 2 millimeter wave base station 200 meters away from each other, and to have a multi-base station scenario, and we scatter almost 3,000 UEs in a street segment, and we had 32 antenna at base station and 8 antenna at UE. So the root mean squared error performance that we get from different channel charting and the different machine learning approach are shown here. The best performance that we get is from mostly Gaussian process regressors. And if we want to compare our approach with the case when if we assume that we have the exact location of UEs, and then we annotate these locations with SNRs, and then just train a neural network or any other machine learning SNR predictor based on ground truth location, we can see that we can achieve very comparable results to the channel chart based SNR predictions. And if we want to take into account the error that we get from GPS, which would be at least around 2 meters, then we will have very bad performance in terms of SNR prediction based on ground truth location. And also, if we use the other adaptive sampling set reduction, which means we find the we find channel chart locations based on the telescopic approach. We will have less complexity, less computation complexity, but we will lose a bit of our performance. And if we look at the computation complexity and number of multiplications that we need in the online phase as compared to root mean estimate error that we get from different dimensionality reduction techniques, we can have this Pareto frontier, where here at the end we have the GPR machine learning regressors, which has the highest computation complexity, but the best thing that we can get, but at the same time we have lower computation, is that when we use TSNE channel charts and we use neural networks here. And also if we use the end-to-end learning, when we use the CSI fingerprint, we couldn't get very good results as compared to when we first make the channel chart separately in an unsupervised manner, and then use this channel chart in a supervised regression problem, and then find the SNR for that. Also, when we have a beam tracking simulation, if we assume that on the right we can see the dominant beam areas for this street segment, and we assume that we have a mobility pass in this street, and we assume that at the first one we will carry on a beam sweeping, and in the rest of the mobility pass we will use either channel chart based beam tracking or the conventional channel beam tracking. So we can see as the area of dominance of one beam is changed, we will face lots of errors in the conventional beam tracking. But if we use the channel charting to fine-tune the beams, even though we will have some errors, which we will show with the black dots, but soon it can get back to the best beam pair and somehow stop propagating the error in this mobility. Then, if we look at the CVF of SNR prediction based for different number of beam sweeping in one mobility pass, here we have the best thing or the exhaustive search, which we have no SNR difference, and then this orange one corresponds to channel chart assisted beam tracking, where we have only one beam sweeping in a mobility pass which contains 60 different steps, and the closest performance of the beam tracking is when we have in every other location one beam sweeping, which is shown by this dashed yellow line. So we can see that we can reduce the number of beam sweepings by using a channel charting SNR prediction in our system. And also here we have the trade-off between frequency of beam sweepings and SNR loss for 90 percentile SNR loss. And here we have our reference, which is exhaustive search. And we can see here with very low frequency of beam sweeping, we can reach the lowest SNR loss in beam tracking. To conclude, what we here considered a channel chart based SNR prediction in 5G millimeter wave networks, and we found that due to autonomous UV beamforming, we may face some challenges in beam tracking, and we showed that by using a channel chart assistant beam tracking, we can get very good results or even comparable very good results. And this channel chart assisted approach shows that we can reduce the overhead and also accurately enable beam refinement for mobile users. And these are the publications which are related to this project, to a part of my thesis. And thank you.
Sometimes ago we discussed about possibility of using combining this technique, channel charting, with self-massive mount systems. I was wondering, did you know this idea or?
No, because I think for channel charting, we assume that point-to-point communication, and also we assume that we know all the base stations. So somehow I'm not sure if we can use it for cell-free massive MIMO.
No more questions. Leave it here. Thank you guys.